Hey everyone, I hope that you all are doing very well. In this section of videos, which is a 2-video series, we're going to be covering how to quantify matter. So how are we going to do this? So basically, in the first video, we're going to be learning how to quantify matter by using and determining our molecular mass, the amount of moles present, and the atoms and or molecules present in a certain amount of a substance using Avogadro's number. In the second video, we're going to be determining the empirical and molecular formulas, because they're different, of a compound using combustion analysis. This first video focuses on the specific methods of quantifying matter using molecular mass, the mole, molar mass, and Avogadro's number, and using these concepts alongside dimensional analysis to derive moles from grams, derive grams from moles, and derive the number of atoms from grams for a given element or compound. Being able to use these concepts to calculate these things, from conversions from moles to grams, grams to moles, grams to atoms, is super important because it's something that you will use basically in every single lab that you have in college. So being able to make those calculations using dimensional analysis and our knowledge of all of those things that I talked about is super important. To figure out how to do all this grams to moles calculations and all those things, the first thing that we have to cover is how to determine the molecular mass of a compound, given the formula for the compound. We can use CHCl3 as an example. So we're given the formula, so we need to use the formula to determine the molecular mass. You might be asking, though, what is the definition of the molecular mass? Well, the molecular mass is the complete mass of a formula or a compound. We can calculate the molecular mass by summing the average atomic masses of all the atoms in the molecular formula. Essentially, it's just all of those, the average atomic masses for each atom involved in the compound summed up together. Asking, where can I find the average atomic mass? Well, if you recall from former videos, we must look to the periodic table to find the average atomic mass. Look at the periodic table tile for hydrogen here. Here, we can see that the average atomic mass is directly below the atom symbol. Right here. And that is what we will be using to calculate the molecular mass. So, all that we will do is sum up the average atomic masses for each of the atoms involved in the molecule. Here's an example of this process. See, there's one carbon, which has an AMU of 12.01, one hydrogen with an AMU of 1.008, and 3 chlorines, which have each 35.45 in AMU, totaling up to 106.35 AMU. When you add all of these together, the molecular mass for the overall compound is 119.37. This is how we are going to calculate molecular mass. It's a simple process, but it's something we definitely should understand because it's super, super useful and crucial that we know it. The concept that we must consider is the mole. First, let's consider the definition. Mole is an amount unit. It provides a specific measure of the number of atoms or molecules in a sample of matter. The important thing about the mole is that the mole it provides us a link between easily measured macroscopic property of a molecular formula, the molecular mass, and the number of atoms, molecules, etc. It is how we get from like grams to atoms. There's the middleman, which is the mole. Grams to moles to atoms. In this way, it's super important for conversions, which we use in the lab all of the time. How does the mole relate to the atom? Any substance, any 1 mole of a substance is equal to 6.022 times 10 to the 23rd atoms or molecules. What is important to note is that 1 mole of any element, any substance actually, contains the same number of atoms as 1 mole of any other element or substance. It is always the same conversion factor where we get 6.022 times 10 to the 23rd atoms is equal to 1 mole of substance. This is a pretty important conversion factor to have handy. The masses of 1 mole of different elements are different because the mass of an individual atom as compared to another one are drastically different at times. The previous example, the amount of mass in carbon was much smaller than the amount of the mass of chlorine. And so that's why we have the mass of 1 mole of that element being different than the mass of the other one. Hence, their molar masses are different. Let's define molar mass really quickly. Our molar mass is the mass in grams of 1 mole of an element or a compound, and is typically written as grams per mole. It's a super helpful conversion factor. Our molar mass is how we get from grams to moles. Again, something that is super useful in the laboratory. So our molar mass of an element is equal to its AMU, which again, we are able to find on the periodic table where I showed you before in this video and in a previous video. So for an element, its molar mass is equal to its AMU. Likewise, the molar mass of a compound is equal to its molecular mass, which is just its AMU of all of its elements involved added up together. So that's why it is so important for us to know how to calculate our molecular mass, because our molecular mass is our molar mass in the instance of a compound. And so with our molecular mass being calculated, we're able to use it for conversion factors of grams to moles. Pause the video now. Here's a very helpful chart summarizing the notes that I just talked about. These are particularly useful, especially when you're considering the elements on the leftmost side of the chart. Final thing to note, which I sort of mentioned already, is that Avogadro's number is how we calculate the units of 1 mole of any substance. So, in this chemistry class, it's how we calculate the number of molecules and atoms in an amount of a substance. So that's why Avogadro's number is super important. Now, in this section of the video, I really quickly just want to cover an example calculation. Other example calculation will be covered in the corresponding problem set for this section of videos. So here's our practice problem. So a packet of an artificial sweetener contains 40 milligrams of saccharin. 40 milligrams C7H5NO3S, which has this structural formula, not super important. Given that saccharin has a molar mass of 183.18 grams per mole, fabulous, they've calculated it for us, 183.18 grams per mole. How many saccharin molecules are in a 40 milligram sample of saccharin? How many carbon atoms are in the same sample? So I'm going to tackle this first question first, and then we'll go on to the second question. Finally, it's important to understand exactly what they're asking for. So this is how many saccharin molecules? How many molecules? The only thing that describes the amount of molecules in a substance, like we said earlier, is Avogadro's number, or the calculation that gets us to their number. Right, so the amount of molecules total is going to be a conversion where we go from grams, which we start at, or we start in milligrams, but we'll do that conversion. But we do grams to moles to the number of molecules of our saccharin. Now this is a pretty typical conversion. Every time it asks you if you want the number or how many molecules or atoms of something and you're given grams, you're going to have to go through moles because of the pathway. So whenever you're going from grams to moles, we're going to divide by the molecular mass. Sorry, not the molecular mass, the molar mass, which is in grams per mole. And whenever you're going from moles to atoms or moles to molecules, you have to use Avogadro's number. As we said earlier, moles is the bridging point. It is what allows us to go from moles of something to molecules or atoms of something. You need moles to be able to use the Avogadro's number unit in our dimensional analysis of this problem. So from grams to moles, you use the grams to moles, the molar mass. And if it's moles to molecules or moles to atoms or moles to whatever, you're going from Avogadro's, using Avogadro's number as a conversion factor. So in terms of setting up this problem, the way I would do this, I'm going to delete some of this here. So we'll have 0.0400 grams of our C7H5NO3S. Apply by our conversion factor, our molar mass, making sure that our grams cancel. See here, we have this in the numerator. We can treat it like a numerator if we write it over 1, right? So we have the grams in the top over here, grams in the bottom over here, so this will cancel out to give us moles. So that's a good first step. What we're going to do in order to convert moles to molecules is we're going to be using Avogadro's number. And we do the same thing here. We make sure that we have mole on the top here, mole on the bottom here, so that when everything cancels out, we're going to have our answer in molecules, which we get again by going from moles to atoms or molecules using Avogadro's number. Now, remembering sig fig rules, which we discussed in a previous video, we're going to have 1.31 times 10 to the 20th molecules of C7H5NO3S. Sweet. So, for the second part of the problem, all we're doing is we're trying to find the amount of carbon atoms that are in the sample. So we already have the total number of molecules, and we can create a conversion factor here. So what I'm going to do here first is erase some stuff. So the only thing to consider really is we look at the formula and we say for every one total molecule, there's 7 carbon atoms. And that's what we use to create our conversion factor. Whenever you're asking how many blank atoms are in the sample, you really just have to look at the molecular formula and create a conversion factor by saying one molecule of saccharin is equivalent to 7 carbon atoms. If you were going, you could do this with other atoms in the sample too. You could say, for every 7 carbon atoms in saccharin, I have 5 hydrogen atoms. So we create our conversion factor and we use it in our dimensional analysis. So we have molecules on the top, right? Say it's over 1. So we put for every 7 carbon atoms on the top, we have 1 C7H5NO3S molecule. So all we're doing is multiplying our 1.31 times 10 to the 20th molecules times 7 carbon atoms. And the answer that this conversion factor yields is 9.17 times 10 to the 20th carbon atoms. Sweet. And there'll be more examples of these types of practice problems, especially because dimensional analysis can be tricky to learn for the first time. Sweet. So the next video in this series is going to be determining empirical molecular formula using combustion analysis. So I'll see you around for that. Have a good one, guys.